So my name is Brent Martin. I'm a senior data scientist at Manaaki Whenua Landcare Research. Say it quickly, it'll be gone next month. And this talk is a little different because it's not going to be a talk about technology, but rather as all the CRIs hurtle towards oblivion if you're a pessimist, or go supernova if you're an optimist, it's a really good time to sort of think about and reflect and share on what we've been doing along the way in our daily life. And so in this case, around the way we've been using AI and deep learning and the way it's evolved. So go back around about 4 or 5 years, and we got into the deep learning space in a real baptism by fire. So we had a project here where we had to, for the Parliamentary Commissioner for the Environment, measure historical green space going back to 1940 in 3 of our cities. Now, it was an interesting project because in the call for proposals, they basically said, what we really want is the data on this, so that's the thing on the right. And we would also like, we think you're going to do this via maps and we think they'd be useful, so that's the thing in the middle. And actually all they really cared about was that Simon Upton wanted to write a really groovy report with some data in it. So they sort of said, we're leading you in this direction. It's a research project, but you'd better deliver. We'd better have the result we want. So that was kind of interesting. The commercial contract had to succeed, but we hadn't done this before. We weren't even sure how to do it, and we had no tooling. But eventually, after a few false starts, we landed on a way of doing this, which is about a way that we could map buildings in historic black and white aerial imagery going back to 1940. We had to get around things like we had no training data. We had to come up with weekly supervised learning and so on. But we got there. And the key thing here is we had to build the tooling as we went. So we built the infrastructure for this as we figured out what on earth it was we were trying to do. And once we'd done that the first time, we started to get other interesting projects coming in, and we started to realise there was an obvious workflow for doing using deep learning to segment. So to take imagery and transform it. We're going to have this problem, are we? Into some other layer. And so that was kind of cool. And so we built a little bit more functionality around that, around things like how do we visualize errors and so forth. Meanwhile, a colleague of mine was getting really interested in deep learning for object detection. He's really into trees and how do we segment individual trees. So he was kind of doing the same thing, and we sort of realized that actually the workflows we were developing were much the same. So out of that, we sort of settled on this common workflow and started thinking about how we could build tools. And the common workflow was simply, we're taking imagery, we're taking labels, we're breaking them into tiles, we're feeding them into something smart, and out of that we're getting rasters that are probability layers of classes, and out of that we end up with a map of some sort. So out of all of that was born the very first version of our deep segmentation, or deep seg. So we built a simple system that says it can take any stack of rasters, it can take in vector files, it does all that tiling and nonsense for you. It generates JSON files with objects in it, and then on the basis of that you can tell it what you want to do. You can do object detection, you can do segmentation, it will spit out your answer, it will give you confusion matrices, and it will do some nice error visualization. Pretty crude. It was a file-based system, so every step of the way it was generating lots of files, and things got a bit messy, but they sort of hung together. Well, eventually, of course, we realised that that wasn't going to get us very far, and so we started on the path of evolution that got us to where we are today. So first of all, we had DeepSeg v0, which I basically built while I was doing the PCE work. Poor code structure because I was in a hurry. Poor use of resources. If you're on NeSI, they get a bit tetchy when you've used 1 million inodes and you run out. If you're not using NeSI, I don't know how many people have ever had a folder on Windows with 1 million files in. The Windows file system starts to seriously break down when you have directories that big and you have to worry about where to put stuff. And the code was fractured in that we were multiple people working on code and not sharing it. So believe it or not, Jan Schindler, who's the chap here, our superhero Jan took that code and code by Alexander Armies, and in one weekend he refactored the entire lot. and he produced DeepSeg V1. And DeepSeg V1, the difference was it no longer generated 1 million files, and he knew how to do remote sensing, unlike me, and it did really cool stuff with remote sensing. After that, eventually we got to DeepSeg V2. This is where we slowed down and said, hang on, maybe we should actually engineer this thing. And we got some more people involved, Simon Planza and Alan Hayes, who's in the room here. And so they started building this thing out into something that was extensible and pluggable and lighter on its resources and so forth. So DeepSeg 2, this is admittedly a slightly old version of it now, but basically with a couple of files, one of them that's the metadata describing how you're going to do stuff, and the other one is the script that runs it. You can literally have a new deep segmentation project up and running and training within 30 minutes of sitting down at your computer, providing you've already got the data. It's really easy to do, and typically what you'll do is you'll copy your last experiment files, change them, and away you go. Won't go through all of that, but that's basically where DeepSeg 2 has got so far. So over time, we've been building out all this functionality to enable us to use it repeatedly and rapidly as scientists. And with that, that's enabled us to scale out. So we're now doing lots of stuff doing deep learning and segmentation. And it's not just about being able to do lots of experiments, but you start to get these really quick breakthroughs, such as over here, we built a model that can generate a land use map or land cover related to land use for all of New Zealand really easily on NeSI. We then noticed that the forestry part of it was really, really good for picking up errors in the existing maps that have been published for the last decade or so. So we were now reusing this model to fix the maps. And then we took another step and realized that actually wilding conifers are pretty much like forestry anyway. And next thing we were using the same model to detect and monitor wilding conifers. And there's various other domains we've been working on as well. So it's just that rapidity of repeat that's enabled that. Finishing up with where we're going with DeepSeg. DeepSeg is great, but it only does a small part of what we want. We tend to build pipelines that are much bigger than that, such as this one, which I'm going to talk about that domain in a second. But also we'd like to be able to share models, share pipeline, metadata, share data, all that sort of stuff. So that's where that's heading. Another problem is getting the data scientists up to speed with how to make this stuff work. People who don't have the experience with the tooling, people who don't have experience with why it goes wrong. And so that's a work in progress, but building out Jupyter notebooks to make this easier and trying to come up with ways where possible that we can visualize what's going on so people can really understand why a model might fail, for example. So jumping sideways slightly, having got to the point where we're internally repeating a lot, we're now starting to build products for customers. And similarly, these things tend to have happened sort of by accident. So this is a product called CamTrap NZ. It's used by quite a few organisations around the country now, and it detects nasties like stoats in imagery. But what happened with this one, again, it started as a research contract. So we didn't even know how well it was going to do, but the client had an expectation that it would be a product 5 minutes later. So we ended up doing very rapid product development, and then fortunately they gave us some money and we developed a user interface. So again, we started with mucking about and we had found ourselves having to really rapidly build something we could actually give other people. But it's been pretty successful. And we have another version of that now where we're experimenting with how to replicate what humans do when they generate landscape scale polygons, that's these things, for soil mapping. So we're trying to teach the machine to do what the person does. And again, there's an expectation that all going well, we'll hand this back to the soil scientists as a product at the end of it. So a bit of a challenge there. Right, big jump sideways now. So that sort of summarises what we've been doing in that space. Now we've got quite a different thing going on, partly because the world's moved on in the last 5 years. So we're now getting into Gen AI. This is happening much more rapidly for us. And one of the reasons is because we got off to a really great start through a collaboration that Nick Spencer and others got together, where Callaghan Institute built us a lovely RAG LLM which that's not the domain we have it in. We have it in the domain of soil science, but it enables you to ask questions and get answers out of some historical journals. It's a really, really great system. They did a fantastic job. It's very open. They gave us the code. You can get in there and you can play with all its parameters, and you can click this button and you can see the thought process that it went through, or rather the data progression that gets you to the answer. So jumping to the punchline, it works really, really well until it doesn't. And what I mean by that is if you get in here and you change any of these, even by a little amount, you can suddenly find it saying, I'm sorry, but I don't know. I don't have any answer for that. And so the issue here was, how can we use a system like that and build it out until we have more confidence about what it's doing? So we looked at their architecture and the information we had, but that doesn't help us a lot. We still don't know where is the secret sauce, what makes this work and not work, why does it break? What if I don't want to use Microsoft or OpenAI that it was built on, and probably because what's it going to cost me if I do that? And could I actually run it locally instead? So this time, instead of starting with experimental, really bad code and working forward, we went backwards. So we started with a beautifully written system by Callahan, and we said, what's actually going on under the hood? And I won't talk through that, but that's what goes on under the hood in a RAG system. And then we just built it in Olama. So now we have a really, really simple system, minimal amount of code. You can change anything you like in 5 minutes, and actually it works pretty well. This is working on open source models and open source libraries. And out of that, we've learned a heap. We've already learned Olama 3.2, small model of only 3 billion parameters, works pretty much as well as the OpenAI one. And that's because we've learned that the search is far more important than the model. So in those RAG systems, getting the search right is really important. We've learned lots about the parameters. We've learned that doing it locally is eminently doable, and that we still have open questions such as, if I was actually to back up a step and not just throw my documents into a RAG system, but actually curate them into better curated data, can I get a step change in the sort of quality of answers? And really, we're only just scratching the surface of what this is going to do for us. The other side of the Gen AI question, why I said it's a step change from what we've done before, is our users, which in my case are our environmental scientists, are already doing it for themselves because the tools are already out there. And so what we've got here is an example of a project going on, Dan Richards, one of our scientists, is doing, where they're interested in using image generation to visualise for humans what different land uses might look like. So essentially they've mocked this up using Midjourney, and then they've done some experimentation. So now we're jumping in behind and asking those same questions. What happens if we use our own local models? How can we solve all these challenges, such as if you try to get stuff done in the New Zealand context using Midjourney, you get some really interesting results. And I don't know how well you can see this, but this is a really typical thing in these big models. They wanted to show conifer plantation, and there it is, it's lovely. But what the heck are all these sort of haystack things here? And they turn up all the time. I have no idea, aliens or something. So how do we fix that? How do we make sure that all the images we produce are really in the New Zealand context and are believable? And there's all sorts of other issues too. Finally, the last bit that we're now looking at, the diffusion models is what everybody's doing, but there's an older technology using conditional GANs, a nice little algorithm called pix-to-pix. And this might actually be really, really useful for us, because one of the things we might be able to do is generate not only images for humans, but geospatial imagery that we could actually then analyse in the same way as we analyse real imagery. And that would open up huge potential. So this is just showing you at the top how pix-to-pix works. If you follow the TensorFlow example here, you can build a little model that you show it an architectural block diagram, and it generates you a photorealistic image of a building, completely imaginary. And the question is, can we take things like the land cover database and generate very, very plausible images of what that landscape might have looked like that led to that classification? And again, there's lots of challenges around how to make that high veracity while giving it enough freedom to actually do interesting things and so on. And then our final moonshot, which is if we integrate a 3D model, can we end up with essentially a digital twin that we can generate pictures of that are fully realistic? Don't know, hopefully. So just to conclude on how we sort of found ourselves where we are, the deep learning for remote sensing, that's all mature and built into our daily work. But the Gen AI stuff is much more widespread and organic. Everybody's doing it already, and it's about corralling and learning and giving them the best tools we possibly can. But I make the case here, it's really, really valuable that we're starting from the ground up. People are deep diving into this technology to solve problems. We're learning how to do that really well, and then we're learning how to upskill everybody to do it. And I see that there's huge potential in this in terms of the impact of our research, that communication that we saw with those pictures, but that scenario modelling type approach where we might take science a step forward, and of course the automation out of all the traditionally expensive stuff we do that's just time consuming and not very valuable. Thank you.
Brent, I think it's a really good example of how collaboration can really progress your research. Any questions from the audience? Yes, Vickings.
Just a really practical one. In one of the slides you showed OpenML. Is that sort of an ML flow variant, or is it an experiment management system, or how does that work?
Sorry, OpenM.
Your future slide.
No, so Open, that's right. That's not something we're doing, that's something we'd like to emulate. I'm not sure if OpenML is still around, but basically it's just showing the general idea. It's a really nice, I could imagine us internally having a space like that if you look at the icons down there. So it's something where you can, essentially a library for all of your models, your data, your workflows as metadata, all that kind of stuff to get rapid reuse.